Welcome back, learners, and in today's video we're looking at another question. And today's question, we have a container, a cylinder container at some radius r, at some height of h, and it's filled with water to some level that's also r, and we were to spin it at some angular velocity of omega. And we spun it so the water went all the way up to the lip of the container without falling out. What is the maximum angular velocity we can spin it at so we don't lose any water? So to begin, we're going to take some position r here and use our basic equation of statics. Change in pressure over our change of position is going to be equal to our density times our acceleration. And we are going to be assuming that our pressure is 0 out there in the surrounding. So rearranging this, we get our change in pressure is going to be equal to density, density times omega squared r dr. Take the integral of those and we get our pressure is equal to density times omega squared r squared over 2. And so we used the acceleration horizontally to find our pressure, but we can also use our vertical acceleration to find that pressure. So that's going to be equal to our density times our acceleration due to gravity at some height of h. And our densities cancel, and we're left with h equals omega squared r squared over 2g. So if we were to take our position of r all the way at the wall, so all the way at the radius of big R, that's going to equal omega squared r squared over 2g. So that's the height of our water, but as we know, height and size is all relative. Like I always say I'm 6 foot because I assume people are asking about how tall I am compared to 3 inches below the surface. So we're looking at the height compared to the bottom of this dip. So we need to find this height to be able to find our maximum height of our water. To find that, we need to look at the change in height of our original size, our height of our water down to the height of the bottom of that lip, and that's going to be represented by d. So our height is going to equal our original height of our water minus the difference between our original and new, plus the height of our water compared to the bottom of the dip. And so now we need to find the change in the water level. So to do that, we have to look at our problem and realize we are losing no water. We're not losing water because it's going to the very top without falling over. So from the bottom of our dip and up, this volume is going to be equal to the volume with the depth of our d and our change in water level. So the volume of that is going to be equal to pi r squared times d, and that's going to equal the volume of our new water level. And now we need to find the volume of this. So if we look at it from, let's say, a top view, it's a cylinder, so it's a circle, and we want to find the volume of some point here. So this circle at some thickness of dr and at some height h. So we're going to have our volume is going to equal the circumference, so 2 pi r, times the height times its thickness. And then we're going to be able to substitute our h's for this. So we get our volume is going to equal 2 pi r omega squared r squared over 2g dr. And if we take the integral of that, we get our volume is going to equal 2 pi omega squared over 2g integral from 0 to our wall, so 0 to our radius of r cubed dr, and that will give us, those cancel, and we get pi omega squared over g times r to the 4th over 4. And now we can plug this back in and get the volume of this one of r squared d is going to equal the volume of this. So pi omega squared r to the 4th or 4g. And if we solve for d, these cancel, that becomes r squared, and we get d equals omega squared r squared over 4g. So now that we found d, we can go back to our equation for our height of r minus d plus hr. So if we plug in for d and hr, we get our height equals the radius minus omega squared r squared over 4g plus omega squared r squared over 2g. Do r over, we get h minus r is going to be equal to omega squared r squared over 4g. And then we just have to solve for our angular velocity now. There's some simple algebra. We get h minus r times 4g over r squared equals omega squared. And then all we have to do is take the square root of both sides, so we get 2 times the square root of g h minus r over r. And that is how we find our maximum, the maximum angular velocity we can spin this at to get our water all the way up to the lip without going over. There we go.